Hi guys, so today we will be talking about ceramics, everything about ceramics on material science for engineers. So let's begin from the beginning. So what are ceramics? Ceramics are they are inorganic, non-metallic materials made from metallic and non-metallic elements. And here in organic, what does it mean exactly? So materials are often divided, like let me just decrease. So let's say we have materials and they are often divided into organic materials and inorganic materials. So what is the difference between them? Organic materials usually contain carbon and hydrogen bonds. For example, we can say plastics. Many of them are hydrocarbons, like rubber or wood, but inorganic materials, they do not contain hydrogen bonds. For example, glass, aluminum, silicon carbide. Do you see anywhere here like carbon hydrogen bonds? No, right? So ceramics are generally inorganic materials. And ceramics are usually combinations of metal elements, like for example, like metal elements are aluminum, silicon, or magnesium, and non-metallic elements. And these examples are oxygen, nitrogen, or carbon. So carbon can be combined with anything else, like you see here, silicon carbide. Just it will not be combined with hydrogen in ceramics. Then, going further, why are ceramics different? Their secret is in their bonding. They contain ionic bonds and covalent bonds. So, let's compare it with metals. And the metals are flexible, but ceramics are not flexible, but they are very strong and very stable. So some examples of ionic and covalent bond. Here we have silicon carbide or diamond, that is covalent bond, and then we have NaCl, that is ionic bond. So let's consider metals. Metals are quite different because we have sea of electrons. As I've mentioned before, we have sea of electrons, and when stress is applied, atoms can slide past each other. So therefore they are ductile and malleable, but it is not applicable to ceramics. So while metals are ductile, malleable, ceramics are quite opposite. They are brittle. Ceramics are brittle. So main properties of ceramics, their advantages that they have high hardness, compressive strength, like you can compress it, but you cannot pull it. It's not strong in that case, but it is strong in the case of compression. High melting temperature, and because they are electric insulators. Corrosion resistance, metal will combine with oxygen and corrode, but it is not going to happen in the case of ceramics. Wear resistance, like they will not be scratched like metals do. Good thermal stability, and as I've mentioned, usually electrical insulators. Disadvantages are very brittle, low toughness, weak in tension, and difficult to machine. And as I've mentioned, the reason why ceramics are brittle, it is all due to dislocations. In metals, material can deform. In ceramics, ionic covalent bond, they restrict the movement. But what exactly happens? In ceramics, atoms have very specific positions. So in ionic bonding, positive and negative ions must stay arranged correctly. If the layers slide, the charges may end up next to each other, and these charges, they don't want to go near to each other. They really don't want to go. So they will start repelling, and it makes sliding difficult. And in the case of covalent bonding, electrons are shared only in specific directions. So the bond act almost like rigid sticks, and they do not easily rearrange. So they are strong but not flexible. And ceramics are brittle because these locations cannot move easily, and the material cannot relieve stress. Like the stress, it will not be arranged properly in the material, in the whole surface. Instead, it will just be strongly applied on one place, and the material will crack. The cracks will grow rapidly, so they have brittle structure, and that's why ceramic mug suddenly shatters instead of bending. So why are they strong in compression but weak in tension? Because in compression, force pushes atoms together. Ceramic atoms like being close together. The strong bond resists compression, and that's why they have very high compressive strength. But in a tension, force pull atoms apart, so tiny cracks, they naturally start forming, as I've mentioned here. And when pulled, cracks open wider, stress concentrates at crack tips, and failure occurs quickly. So it has low tensile strength. And examples, we have concrete alone is poor in tension. That's why we are using reinforced concrete using steel bars. So let me show you. So we have reinforced concrete. You see here, so we have we have a steel bars under the concrete, because again they have low tensile strength. That's why the ceramic alone is not enough, because you can see that if it's going to be just plain concrete, the cracks will form easily. But if we have reinforced concrete, the material is going to be way stronger. So we have then different types of ceramics. We have traditional ceramics here, and the traditional ceramics usually made of natural raw materials. So traditional ceramics are made of natural raw materials. So examples, we have clay, we have silica, we have feldspar. And typical process, let's say how we make clay: water, shaping, drying, firing. So examples, we have bricks, roof tiles, pottery, porcelain. These all are natural ceramics, traditional ceramics. And then we have advanced ceramics. They are made from highly purified powders. Ceramics are made from highly purified powders. Like examples, we have alumina, silicon carbide, silicon nitride, coron nitride, zirconia, and so on. And what is the difference in manufacturing? Like in traditional ceramics, we mentioned that it is just like water, shaping, drying, firing. But in advanced ceramics, it is fine powder, controlled mixing, precise shaping, and high temperature sintering, which I'm going to further mention. So advanced ceramics are engineered for specific properties, like their applications are way more advanced, like in electronics, in aerospace, in biomedical implants. So Next we have glass here. So glass is special, and how exactly glass is made. By the way, glass is different because most of ceramics they have crystal structure, but glass has amorphous structure. So in crystal structure, the atoms are arranged in a specific pattern. Like you can notice the pattern, but in amorphous, there is usually no specific no atom pattern that you can catch. So how exactly glass is made? We have the main ingredients are silica, soda, and lime. So the process is we have this in raw materials and we melt them at very high temperature, and then we form desired shape and we perform controlled cooling. And unlike most ceramics, glass does not crystallize. So um, why do we add each of this? There is a reason. Silica is main ingredient of glass, usually around 70%. And we add soda because it lowers melting temperature. Otherwise, it would be very hard to make glass, because if the melting temperature is high, then too high, then of course it will be way more expensive to generate all that heat and energy to uh, make the glass. And lime improves durability, so it is less breakable, I would say. And the most common glass we have is soda lime glass, and it's used for windows and bottles. So this is the composition of soda lime glass. And then we have borosilicate glass, which contains boron oxide. So examples, the main difference between borosilicate glass and normal glass is that it has better thermal shock resistance. So we use it in Pyrex, like when we are baking something, we use that kind of glass. Or in laboratory, we use that kind of glass. So this boron oxide, it changes everything. And then I would like to talk about special ceramics. So first we have alumina in our special ceramics, one of the most important engineering ceramics, and the property is that it is hard, wear resistant, corrosion resistant, and electrical insulator. So where we apply them, we apply them in cutting tools, grinding media, spark plugs. Then we have silicon carbide. It is again very hard, temperature resistance, and we use it in armor, abrasives, furnace components. Then we have silicon nitride. It is strong, but it is tough for ceramic, and it is thermal. It has thermal shock resistance, and we use it in tubing parts, bearings, engine components. And then we have refractory ceramics. So these ceramics are designed to withstand very high temperatures, and we use them in steel making, furnaces, kilns. And I would like to show more about refractory ceramics. Just a minute. Okay, so I'm going to show you examples of refractory ceramics. So as you can see, like they are very heat resistant, as you can see from here. High melting point, thermal shock resistance, corrosion resistant, and high strength. So these are refractory ceramics. Okay, moving on, we have cement. What is cement? Cement is a powder and acts as a binder when mixed with water. And chemical reactions occur, the cement hardens. And the most common cement is Portland cement. It is made from limestone and clay. And the manufacturing process is grinding, heating in rotary kiln, clinker formation, grinding with gypsum, and final product is Portland cement powder. And then a lot of things students confuse is cement and concrete. Cement is just a binder, like flour in a cake, but concrete is final product. It contains cement, water, sand, and gravel. Now I want to talk more about porcelain. Actually, it is one of the really common types of the ceramics, and it is very aesthetic, and you can see the porcelain is really beautiful and expensive. So what is it? It's high quality ceramic. It is made from kaolin clay, feldspar, and quartz. It is white, dense, low in porosity, and we use them in plates, cups, and their electrical insulators. Now I want to talk more about ceramic processing. Let me see if I can show you something interesting on ceramic processing. Ceramic processing. Okay, as you can see here, that's really cool. So first we have powder preparation. What is this? We have raw powders selected, particle size is controlled, and smaller particles generally improve sintering. Then we do mixing. The purpose is to ensure uniform composition, and sometimes additives can be added, such as lubricants or binders. Then we have shaping. So we have many types of shaping. We have pressing. So powder compressed in a die. It's used for simple shapes. Then we have extrusion. Material forced through an opening, like squeezing a toothpaste, like injection molding, and used for pipes or bricks. And then we have casting. Liquid slurry poured into a mold, and we use them for complex shapes. And then we are drying them. So water is removed. It prevents cracking during the firing. And then we do firing. High temperature treatment. Several important things happen. Sintering, vitrification, and strength increase. So we will talk more about them, but first I want to show you each type of shaping that can be used. So we have here shaping. Okay, so you can see that's how the pressing happens. We just put it in such a machine, and then we just force them down. And then we have extrusion, which I want to show you as well. Okay, so this is how extrusion happens, just so you have information. Like here we have plunger, heating plate, layer wise curing, and so on. And lastly we have casting. Casting is way different. We kind of mix them together. Yeah, you see here, we mix them with they're in liquid form. Okay, So moving on, I want to talk more about firing. So what is firing? Firing, as I mentioned, it brings us sintering. Sintering is one of the important concepts. It is heating particles below melting point so they bond together. And during sintering, what happens? Particle next form, pores shrink, and density increases. So it gives us higher strength and higher hardness. And then we have vitrification. It's formation of a glassy phase during firing. Like part of ceramic becomes slightly glass-like. It gives us lower porosity, better water resistance, and greater strength. So I want to show you about a bit more about sintering and vitrification because I'm a visual learner. Sintering. Okay, look what sintering does. It binds the powder together, and vitrification. Okay, vitrification of ceramics. Yeah. So it is like bringing a bit of glass-like structure, though I cannot find the. Oh, you see here, you see the difference between ceramic tiles and vitrified tiles. You see the difference? One is a bit having glassy face, like glassy structure. So that's what I was trying to show you. Okay. And then I want to talk about porosity. What is porosity? Amount of empty space inside ceramic. If we have high porosity, it is lower strength, higher water absorption. And low porosity, it means stronger, more durable, and better wear resistance. Okay. So, and lastly, I want to talk about thermal shock. It is damage caused by sudden temperature changes. So, example, very hot ceramic placed in cold water. So, why does it happen? Outer layer of ceramics, like let's say this is a ceramic, like a vase, and like outer layer, it cools faster than inner layer. So, it's still like hot here, but the outer layer already starts cooling, and different parts they contract differently, unevenly, and then stress develops and cracks form. So this is, and the good thermal shock resistance examples are borosilicate glass, which we use in like Pyrex, and some advanced ceramics. So this is all I wanted to talk about ceramics. Thank you for listening and have a nice day. Goodbye.